Hello, ladies and gentlemen, and welcome back to another APE screencast with your AP Environmental Science teacher, Mr. Stano. And today we're going to go on to energy flow and matter recycling within our environment. Energy flow, if you notice from this diagram, you can see here that you could start pretty much anywhere. We'll start with our decomposers, favorite type of organisms, and you can see that the energy moves. Now, as it moves, we have heat given off. And you notice that at pretty much every single step, heat's given off. So even solar energy is coming in for the producers are eaten by consumers, heat's given off. And then as our consumers get eaten by our decomposers, heat's given off. So we always have a loss of energy as heat within this system. But if you also look, these compounds are going to be making their way all the way back around again, getting recycled. We're dealing with a finite place. The Earth is only one Earth. All the materials here are all the materials here. That's it. We have a finite amount, so it's got to stay here within this planet so that basically life can go on. Energy flow within ecosystems, like I was showing earlier in that previous slide, shows how that we have this movement of energy through the different trophic levels. So we have our producers as our first trophic level. And then as we move up, your primary consumers are your herbivores, your second, and then moving into our consumers at our third and fourth trophic level. Notice each exchange that we have, the heat loss. Extremely important to recognize that we have heat loss at every single step. It doesn't matter which one it is, there's heat loss. Same thing that we're going to see within food webs. Now, in these food webs, it's just interconnected food chains, just a little bit more complicated, but the arrows are showing the direction of energy flow. So if we start here with our phytoplankton, they go to our zooplankton, to squid, and we'll just go right to the penguin. But at each step, we would have a loss. Some heat energy coming off. Even if we went right up to the top, even getting to humans, there's going to be a loss. So if you look at, by the time we get to humans, how much heat energy has been lost as we get all the way up to the top. So what this is all about is the second law of thermodynamics. Basically, there's a decrease in the amount of energy available to each succeeding organism in a food chain or web. That's it. As we go, that first law of thermodynamics basically say energy can't be created nor destroyed, which it's not. It's just as we go from one organism eating another to eating another and moving through, the organism needs some of that energy for maintaining itself, reproduction, living. So that is lost. We can't use that for the next organism. That second law of thermodynamics is kind of taking care of that. What ends up happening is that there's only a certain amount of energy available to the next trophic level, or ecological efficiency basically says there's about 10% transfer of energy from one level to the next. In some systems, it's a little bit more. Some systems, it's a little bit less. So here, if we start at the bottom with our producers, here's the amount of energy that's there that they've taken in from the sun. As our primary consumers or zooplankton eat it, notice we only have 1,000 units. We've lost 90% loss, only 10% gain moved up. As we move into our secondary consumers, same thing, only 10% moves upwards. Finally getting to tertiary consumers, our humans, 10%. So as we move up, all this loss of heat. And right here we have our decomposers on the side, but you can see even with them, heat loss right there. So ecological efficiency, roughly 10%. So for most examples in this class, we'll be using 10%, sometimes as low as 2%, sometimes it's a little bit more, but whatever the case may be, it's basically the amount of energy that's available to the next level. Which brings us to the productivity of our primary producers. GPP, or gross primary productivity, is the rate at which an ecosystem's producers convert solar energy into chemical energy as biomass. So if we look at this map of the United States, we can see in areas where there's a huge amount of water supply and also sunlight, our productivity is increased. Look all along the West Coast. Same thing, huge amount of water supply. A good availability of sunlight is going to increase our productivity. Even here in the Northeast, productivity is high. But notice as we move farther and farther north that generally speaking, the productivity will decrease just because the sunlight is going to be less and less. But the problem with gross primary productivity is it accounts the energy that basically is converted, but not available to the next level. That's where our net primary productivity comes into effect. So net primary productivity is the rate at which producers use photosynthesis to store energy minus the rate at which they use some energy through respiration. So what this says is, all right, we know that photosynthesis is going on. We also know that the organism's using some of that energy. So if the next trophic level were to eat that organism, how much energy would they get? So that's the net primary productivity, is basically looking at that. So if you look at this diagram, we have this photosynthesis going on in the leaf. It uses respiration is the energy loss, but growth and reproduction from that leaf, and that's our net primary productivity right there. Gross primary productivity is basically all the photosynthesis going on, but it doesn't take anything else into account. The net primary productivity takes into account that growth and reproduction. If we look at net primary productivity all across the globe, we can definitely see that some areas are more productive than others. Net primary productivity is measured in kilocalories per meter squared per year. So amount of energy per area over a given time. We see that our estuaries, swamps, marshes, and tropical rainforests pretty much outshine all the other types of ecosystems as far as their productivity. There's a good reason for this. Estuaries, usually there's a high amount of water there. They have longer growing seasons, but also a huge amount of nutrients come into estuaries. That influx of water coming in and out of the different types of water, salt and fresh water, just make them highly productive areas. Swamps and marshes, the same thing. High amount of water available, longer growing seasons, huge amount of nutrients coming in to the system, also being recycled within the system. Tropical rainforests, on the other hand, they have extremely high amount of sunlight. They also got a huge amount of water going in, but the recycling of nutrients is extremely fast there. They are productive, but extremely fast nutrient recycling within that system. We'll go more into the net primary productivity of some of these systems. So speaking of nutrients, soil is a renewable resource. This is where it holds the nutrients that allow plant growth to occur. It also helps purify water. Soil formation begins with bedrock that's broken down by physical or chemical means or biological processes, weathering, what we learn in earth science. As time goes on and more weathering occurs, soils begin to mature and they start to have distinct layers called soil horizons that we're going to see in the next slide here. So here's our basic soil horizons. So if we look at mature soil, so this is something that's been weathered for a long period of time, we have our O horizon up on top. Okay, so that's our organic layer. Our A horizon, it's our topsoil. B horizon, subsoil. And notice there's a little bit of change in here in our C horizon, parent material. So our C horizon is kind of like this bedrock layer right here. The B horizon is broken up rock. A horizon, more finely broken up. And then the organic material up on top within our O horizon. Notice it changes. In younger soil, the regolith is going to be a bigger area, or that C horizon, where that bedrock is, where it's broken up, is going to be bigger. Same thing with really extremely immature soil. But what also happens is that in different areas, this rate of weathering is going to be different due to whatever external factors there are. So we'll get different types or different, I would say, characteristics of each horizon. There's a couple of things that we see within mature soils. Infiltration is the downward movement of water through the soil. It's actually the infiltration is that movement from basically like the surface into the soil. Percolation is that movement down. Then we have leaching, which is going to be dissolving of minerals as that water carries them into lower layers. And that leaching, percolation, and infiltration will basically determine your soil quality. If we look at different areas around the world or different types of biomes, we see changes or differences within the soil profiles. And I just want you to see that they're different in the different types of forests or biomes that we have. Some other soil properties that you should be familiar with is the permeability. So depending on the particle size, the porosity is going to be may change a little bit if it's compacted or not. So we have our porosity, our permeability, porosity and permeability, and looking at any other infiltration rates that we may have. Permeability is basically how rapidly that water can go through. Porosity is the percentage of pore spaces. So all these are determined by the properties of the actual material there. Yeah, just taking a look at them again. And that's about it. I'm going to hold off here before I go more into the nutrient cycles. I hope you enjoyed this screencast. Take care.